Hello guys, welcome on Tesla Eduventures. In this video, we are going to discuss the series LC circuit. So you can see this is a series LC circuit, and in this circuit there is a series combination of capacitance and inductance. Both are connected in series with this voltage, and you can easily predict that what I'll say first of all, that we could not add up these two voltages like this simply because obviously VL and VC are not in the same phase. Okay, and we have to draw the phasor diagram to add up these voltages. So let us draw the phasor diagram. So this is a phasor diagram of this circuit, and this is drawn at t is equal to 0. So at t is equal to 0, we can easily draw the phasor diagram, and we will be placing the current on x-axis because current is a reference physical quantity here. As we know that in series circuits, current remains same. And we know that the voltage across inductor is ahead of the current by a phase of pi by 2. So we will be drawing the VL over here like this, and voltage across capacitor is behind the current in the phase by a phase of pi by 2. So we'll be drawing VC here. So we can say that the net voltage, see, first of all, there are two things. If we are considering high frequency circuit, this is a high frequency circuit. If this is a high frequency circuit, then XL, which is omega L, and XC, which is 1 upon omega C, and obviously omega is high on high frequency circuit, so XL will be greater than XC, and therefore we can say that VL will be greater than VC. So if this is a high frequency circuit, then VL will be greater than VC. And obviously, if you are thinking that at how much high frequency this occurs, so I can say the frequency must be greater than the value where XL and XC are equal. So if the frequency where XL and XC are equal is omega naught, then at high frequency, omega should be greater than omega naught. And at low frequency, I can say that XL will be less than XC and VL will be less than VC. So for a solution purpose, I am assuming that frequency is high, and therefore the net voltage will be this, and this would be VL minus VC, and this is current. This phase is pi by 2. So this is the net voltage, and we know that the net voltage V will be equal to VL minus VC, and V can be written as IZ, while VL can be written as IXL and VC can be written as IXC. Cancelling this I with I, Z is equal to XL minus XC. This is the value of impedance in this circuit. And impedance is the combined resistance offered by the circuit to the current. So this is the impedance. And now if we write down the equation of current as a function of time, so we will be writing it down as I naught sine omega t plus minus phi. So first of all, we can say that I naught is the peak value of current, and the peak value of current is V naught upon Z. So V naught upon Z is this one. So this is V naught upon Z, and this is sine omega t plus. Now you can see that we have already assumed that this is a high frequency circuit, and in this high frequency circuit, VL will be greater than VC, and therefore net voltage will be VL minus VC. So as you can see that the net voltage is ahead of current by a phase of pi by 2. So, and we know that the phase of net voltage is omega t. So we can write down that the phase of current will be omega t minus pi by 2. And therefore we know that if we take a negative as a common sign, so it would be sine pi by 2 minus omega t, and this can be written as cos omega t. So this is very simple, that I is equal to minus V naught upon Z cos omega t. This is the current flowing in this circuit. And if you talk about the power, so average power loss, obviously, average power loss will be equal to 0 in this circuit, and it is very clear that it would be 0 due to the fact that cos phi, which is the power factor, is 0, as phi is 90 degree here. So cos phi is 0, and this is the power factor. So the average power loss in the circuit will be 0. And this is quite obvious that there is no presence of any resistance in this circuit. This is a pure inductor, this is a pure inductor, this is a pure capacitor, and there is no resistance of this connecting wires. So there is no presence of resistance in this circuit, and this is an ideal circuit, and therefore there is no loss of heat in this circuit. So as there is no loss of heat in this circuit, we can easily say that the power loss, average power loss in this circuit would be 0. So thank you guys. In the next video, we'll be discussing the parallel combination of these two LC, L and C. Thank you.